Is it faster? I will try to show you a way that's faster. I cannot, yeah, let's try it. Okay. All right, so let's put in our knowns. So this whole thing is 20. This is 18. I will definitely be able to go faster. And so will you. And this one is 10. All right, and our job is to find a D, which is this whole thing, and this is a question mark. Okay. I think it might be faster if instead of putting the variable near the question mark, actually put it on the opposite side of the circle.
What?
And then walk both ways around the circle. Okay, so how about this? Why don't we start right here? And we're just gonna call that X. Okay, and if that's X, isn't there something else that's X? Right, this piece right here is also X. Okay, let's walk counterclockwise around the circle first. So if that's X, how big is this piece next to it? 20 minus X, so therefore this piece, so if this is 20 minus X, this piece is also 20 minus X. And I am done walking in that direction. Okay, because I got something in the part that I need. Now let's walk the other direction. So if this is X, how big is this piece right here?
18 minus X.
Yeah, that one will be 18 minus X. So therefore this one will also be 18 minus X. Okay, we do have to do this process once. So if this is 10 and this is 18 minus X, we need to figure out this piece, which would be 10 take away the 18 minus X, which would end up being 10 minus 18 plus X. Okay, so negative 8 plus X.
Can you just do 8 minus X?
Oh, sure, yeah, negative 8 plus X or X minus 8. So now the pink thing is the green plus the red.
Oh, it's 12.
Yeah. So this is 12 because it's equal to the 20 minus X together with the X minus 8. The X's cancel each other out and you get 20 minus 8. So did you find that one to be a little bit easier? Yeah, so the weird part about that is that you start with the variable opposite the thing you wish to find, because then you're only walking halfway around each direction. So, all right, so you'll have a chance to try that on your homework. Let's talk today about arcs. Now, arcs are portions of the circumference, and we will talk about measuring arcs in two different ways. The first way that we can measure an arc is based on its degree. The other way we could measure it would be a portion of the circumference. That would be called its length. Today we're only talking about its measure, so it will always be in degrees. Now, to be able to talk about this arc, we have to know about the angle that it comes from. And the angle that it comes from is called a central angle. If the rays have their vertex at the center. So a central angle is an angle with its vertex at the center of a circle. With its vertex at the center of the circle. Now, pretty soon we will see angles that are not like that. So we might see an angle that's like this. That's not a central angle because its vertex is on the outs, like on the circumference. All right, so a central angle has to be at the center. We will always tell you what the center is, and that is communicated like this. Circle O. Okay, so a little circle symbol with a dot, and then the letter that is the center point. So angle AOB is an example of the central angle, and it correlates to arc AB. So when we are naming arcs, we just use this like arch thing on top of the letters. But if I said, okay, walk around the circle from point A to point B, hopefully you would turn to me and say, well, which direction do you want me to go? Because isn't there like a short distance or a longer distance?
Yeah.
So we have to be able to have a way to communicate with each other so that we can clarify, I want you to go to the shorter distance, or I want you to go to the longer distance. We call those two different things. The shorter distance is the minor arc. All right, so a minor arc is the shorter distance along the circle between 2 points. And so if it's a minor arc, it will always be less than half the circle. How many degrees are in a full circle? Okay, so then half of that would be 180. So a minor arc will always be less than 180 degrees. So basically, if I tell you that this angle is 60 degrees, you know that the measure of AB would also be 60 degrees. So we can actually refer to this curved edge, this crust of the pizza, if you will, with degrees. We're going to say it's a 60-degree arc. Now, a major arc would be the longer distance around the circle. So the longer distance around the circle between 2 points Oh, Elliot, you've thought of the one exception. So he's like, well, what happens if the 2 points are at the halfway point? In that case, we can't call it major or minor. We have another word for it in that case. It's a semicircle, yeah. Or, you know, since it's a half arc, like half circle arc, it's a semicircle. So in this case, when we are naming a major arc, this is important. We will have a third point. All right. Okay, thanks. We will always have a third point to indicate that you went the long ways. Longer name means longer way. Longer name means longer path, longer arc. That major arc will always be greater than 180 degrees. So if I tell you that this is 60 degrees, how big is this arc here? 300 degrees. Okay, that would be a 300-degree arc. Alrighty, so semicircle is if you have an arc that is connecting the endpoints of the diameter. So an arc connecting endpoints of diameter. The diameter is going to be your friend. Always look for diameters. Okay? They give you a lot of information. The semicircle will always equal 180 degrees. All right. So you've already sort of seen me do this, but the measure of the arc is equal to the measure of its central angle. So it equals the measure of its central angle. The math here is not particularly hard. Everything always adds up to 360. So if we want to find the measure of each of these, all right, if we're going from T to Q, how long would what would be the measure of that arc? 120 degrees. What about S to R? Let's see. Uh-oh, that's the one we don't know.
100.
It is 100. Can you find yourself a diameter? Can you see that that's 80, and therefore this must be 100? See how diameters are going to help you. So that's 100. What about TQR? T to Q. It is the long way, good, because there were 3 letters. It's still just a semicircle, so that's 180 degrees. What about Q to S? Short way. So Q to S, short way, right? And the reason I know this is the short way is because there's only 2 letters. Because 2 letters. And so that would be from Q all the way to S would be 160. QRT, oh boy, Q to R to T. Well, isn't that everything except 120? So that's one quicker way to do that. So it would be 240. And then T to S to R, that's also a diameter. Goes from one end to the other, so that's 180. See, so I thought you would probably find this mathematics to be a little bit simpler.
Sure is.
We will ask you to consider what congruent circles are. So on this diagram, you should have found 19 congruent circles in here, and then the 20th circle would be the one all the way around the outside edge. All right. If you didn't see 19, then go back, make sure you can see that there are 19. Now, what do you think makes a congruent circle a congruent circle? Like, if I have one circle in this hand and one circle in this hand, how would I be able to call them congruent circles?
Same size.
Okay, same size. So what am I going to do? Like, lay them on top of each other? What could I be told so that I would know that they're the same size? Same radius. Good. So they must have congruent radii. If they have congruent radii, then they are automatically congruent circles. So this design, as ancient as it is, I mean, I think this design is even in the Kabbalah. This design is in temples and churches all around the world. This design was used by Leonardo da Vinci to produce a lot of proofs. So we're going to be talking about that quite a bit. And the idea that it comes from congruent circles is the primary basis of the proof. Now, if we want to talk about arcs being congruent, arcs will be congruent only if there are 2 things in place. So let's say you get the cheese stuffed crust of a pizza. Okay, like you get a pizza with the cheese stuffed crust, and you really only care about the cheese stuffed crust. Okay, so the rest of the pizza you don't care about, somebody else could have that. You want that cheese stuffed crust. Now, let's say I go and buy a pizza, and Sarah goes and buys a pizza, and Abby's gonna get to pick the crust. All right, so she wants the biggest amount of crust. How are you gonna decide whose pizza to get that from? Whoever has the biggest pizza. So obviously, one of the factors here would be the radius would matter, okay? So one of our factors would be, if you want, okay, so let me keep going with this analogy. So let's say our pizzas are exactly the same size. Okay, so now you need to pick a piece, you know, so that you get the biggest crust. Well, what are you going to think about?
How to cut the biggest slice.
How to cut the biggest slice. Okay, but let's say I cut them all in equal. Let's say I cut it in equal
Take all the
thirds. I cut it in equal thirds. So hers is cut in equal thirds. My pizza's cut in equal thirds. Which piece are you going to pick? I mean, doesn't it kind of? You're like, I don't know. I just want the cheese crust.
I want the cut.
What I'm trying to get at here is that there were 2 things that mattered. It didn't just matter whether the radius, you know, the size of the pizza. It also mattered what size did I cut those slices. So the angle will also play a role. So if we cut them in equal thirds, like her pizza was cut into equal thirds, my pizza was cut into equal thirds, then in theory, all those crust pieces would be congruent. Okay, so there's 2 things that matter to have congruent arcs. First, radii must be congruent. And secondly, the central angle must be congruent. Central angles must be congruent. Because obviously, if the central angles were different, she would pick the biggest slice, the one with the biggest angle, okay? Because that would have the biggest arc. So just, that's the pizza analogy. So right here, in this particular example, would arc AB be congruent to arc CD? Okay, so yes. Now, if you had to explain, use those two reasons from the previous slide. You would say first, the radii are congruent. Radii are congruent because it's the same circle. And then secondly, you would say central angle is 80 degrees. So central angle is 80 degrees for both. So what about the second example? Is arc AB going to be congruent to CD? So is this arc here going to be the same as this arc here?
One has not the area. Oh no, it's the radii. The central angle.
They're both a quarter of the pizza, but wouldn't you want the larger pizza? Wouldn't you want the quarter cut from the larger pizza?
Yeah.
Okay, we're thinking only about the crust here. So this one's obviously larger because it comes from a larger radii. So are the arcs the same length? No. All right, AB, arc AB is going to be greater than arc CD because the radius is bigger. Radius of AB of the circle that has AB is greater. So I'm just going to say the radius to arc AB is larger. See? So like this radius is much greater than this radius right here. Okay? The central angles were the same, but you have to have both of those pieces. All right, so then what about this? Are those arcs the same?
Yes.
Yeah, because they come from congruent circles. The radii are the same and the central angle is the same. All right. So 9.2 should be pretty easy peasy. Please go back and look at 9.1. I'm going to answer questions about 9.1 tomorrow.